Today we will discuss a test which is related to the soil. It is a test which is named as the unconfined compression test of the soil. The unconfined compression test is a laboratory test used to derive the unconfirmed compressive strength of a rock specimen or a soil specimen. Unconfirmed compressive strength stands for the maximum axial compressive stress that a specimen can bear under zero confining stress. Now there is a need to discuss that what is the axial compressive stress. Axial compressive stress refers to the compressive force per unit area applied parallel to the specimen to the longitudinal axis of the material or the structure. It is a type of normal stress that causes a material to compress or shorten in the direction of the applied force. Axial compressive stress is typically denoted by the symbol of sigma and it is measured in the units of force per unit area. We have discussed a term zero confining stress. Zero confining stress refers to the condition where a material or soil is subjected to no lateral restraint or confinement, allowing it to expand or deform freely in all directions except the direction of the applied load. Unconfined compression test determines the compressive strength of the soil and other materials. It measures the maximum stress a material can withstand without confinement. Here we have the objective. The primary purpose of this test is to determine the unconfined compressive strength, which is then used to calculate the unconsolidated, undrained shear strength of the clay under confined conditions. We have then scope for the test. For soils, the undrained shear strength is necessary for the determination of the bearing capacity. Here we have the key word, the bearing capacity of the foundations, dams, etc. The undrained shear strength of the clays is commonly determined from an unconfined compression test. Unconfined compression test gives undrained shear strength, which we have discussed earlier that it has a symbol of sigma, of cohesive soils that is useful in determination of the bearing capacity of the soil, stability of the earthen dam, embankments, and then we have the cohesive soil is used in the core of earthen dam. Here we have the apparatus. First thing we have the compression device. Here we have the compression device, load and deformation dial gauges. Here is the load gauge. Here we have the deformation gauge. Sample trimming equipment which is used to made a sample in this mold. Here we have a balance and a moisture can which is used to have the moisture content of the soil. Coming towards the most important part of our test, which is our procedure. First we have to extrude the soil sample from Shelby tube sampler. Then we have to cut a soil specimen so that the ratio L by D is approximately between 2 and 2.5, where L and D are the length and diameter of the specimen respectively. First we have to determine the mold volume, which can be denoted or which can be extracted by measuring the diameter and length. Usually we have given the diameter and length of the mold in which we have to make our sample. Then we have to calculate the total mass of the soil we have to take for making our first sample. We have given the moisture content, or we can also calculate the moisture content of the soil from the electric oven and then we have to make use of that moisture content for adding water in our sample to make our sample. Then we have to measure the exact diameter of the top, which we have discussed earlier, at three different locations 120 degree apart, and then make the same measurements on the bottom of the specimen. Measure the exact length of the specimen at three locations 120 degree apart, and then average the measurements and record the average as the length on the data sheet. Then we have the weight the sample and record the mass on the data sheet. Calculate the deformation A and corresponding to the 15% strain. And these two are the symbols of deformation, and here is the symbol of strain. Then we have to calculate the original specimen length, which will be denoted as L0. Then we have to carefully place the specimen in the compression device and center it on the bottom plate, and then adjust the device so that the upper plate just makes contact, not applying pressure. It only just make contact with the specimen, and set the load and deformation dials to 0. This is very important part because we have to calibrate both the load and deformation dials to 0. Apply the load so that the device produces an axial strain at a rate of 0.5% to 2.0% per minute, and then record the load and deformation dial readings on the datasheet, and at every 20 to 50 divisions on the deformation dial. Keep applying the load until the load decreases on the specimen. These are the three conditions which denotes that how much time we have to keep applying the load. These are the three conditions. First condition is that the load decreases on the specimen significantly, that the dial reading will decrease significantly. Second condition is that the load holds constant for at least 4 deformation dial readings. We will while performing the test, we have to write both the load readings and deformation dial readings, and when the load holds constant for at least 3 or 4 deformation dial readings, we have to stop our test. Number 3 condition is that the deformation is significantly past the 15% strain that was determined in step number 5. Then we have to draw a sketch to depict the sample failure, which is between the stress strain, and then we have to remove the sample from the compression device and obtain a sample for water content determination. Computations and interpretation. The undrained shear strength of a cohesive soil is equal to one half the unconfined compressive strength when the soil is under friction, when the soil is under 0 degree friction angle. Here we have the angle of friction. The most critical condition for the soil usually occurs immediately after the construction, which represents an undrained conditions, when the undrained shear strength is basically equal to the cohesion. This is expressed as this. Here is our mathematical formula, where C is the cohesion and QU is the unconfined compressive strength divided by 2, and SU is the undrained shear strength. First step, when we have to calculate the results, or when we have to compile the results of an experiment, the first step is to convert the dial readings to appropriate load and length units and enter these values on the data sheet in the deformation and total load columns. Then we have to confirm that the conversion is done correctly, particularly proving dial gauge readings conversion into load. We will be given a proving ring constant to convert those dial reading into the load. Compute the sample cross-sectional area. Here we have the pi by 4 into d square, which is the formula of area. D square is the diameter, and it will be given in the starting of the test. Then we have to compute the strain from this formula. Here we have the symbol of strain. Delta L is the change in length divided by the original length of the specimen. Original length will be determined before testing or before carrying out our experiment, and delta L will be determined after the deformation of our sample. Then we have to compute the corrected area. Here is the formula of corrected area. A dash is the corrected area is equal to A naught, which we have calculated earlier, sample cross-sectional area, divided by 1 minus strain, which we have calculated here. Then we have to calculate the specimen stress. Here we have stress is equal to pressure over area. Area we have to take here usually students make a big mistake that they take the area of the cross-sectional sample. In fact, here we have the area of here we have the corrected area to calculate the stress. Compute the water content, which we will have from electric oven. Plot the stress strain curve and show QU, which is unconfined compressive strength, as the peak stress. Be sure that the strain is plotted on abscissa. Here we have the table in which we have to write our readings. First we have the deformation dial reading, then we have the load dial reading, then sample deformation. Here we will have the sample deformation delta L. Then we have the strain, which we will calculate from this formula. Then we have the corrected area A dash and load, which will be converted from here load dial reading by multiplying it with the proving ring constant. Here we have the load kilonewton, pounds will be converted into kilonewton. Here we have given the proving ring constant 4.6 into 10 raised power minus 3, and then we have to calculate the stress by using the formula P over A dash using corrected area. Here we have the axial stress kilopascal and axial strain. We have discussed earlier that the curve will be plotted between the stress strain, and here there is a need to tell the relation between the stress strain. The stress strain relation is a fundamental concept in material science and engineering, describing how material responds to external loads. We have a graphical representation between them. The stress is the force applied per unit area, measured in pascals or pounds per square inch, whereas the strain is the deformation or change in length per unit original length, expressed as a dimensionless ratio. Here the peak value denotes the QU, which is the uncompressive shear strength, which then divided by 2 will give the undrained shear strength. Thanks for watching.